will walk through my process for determining the best location of ponds at the landscape scale. The first step in this process is to generate a good base map. And this base map should include all of the area that you're going to be working under. The elements of the map need to include property bounds, as well as a good modern aerial image. We also need to be able to access contours or topography. This will show us the landform that we're working with. We also need soils data. So this data will tell us about the particular soils types that we're working with, as well as types of information really relevant to the construction of our ponds. We can use this base map to help us find optimal pond locations. And following this initial assessment, we want to take a good look at the sites on the ground. This helps us narrow down the possibilities on larger properties and really get to quite rapidly some decision points around where we might be wanting to place these ponds in the landscape. But following this initial analysis, we will take on more targeted analysis at the site level, and we'll talk about that as well. There's many ways to make a base map, from doing on-the-ground survey with hand tools and drawing a map with pencil and graph paper, to sourcing pre-existing maps for a site, to utilizing online GIS sources to make a digital map, to collecting your own digital data and running it through a GIS program to create your own map. Usually, when I'm working on a bigger project, I will follow the latter approach and collect data that I can utilize in a GIS software. We use QGIS, which is an open source mapping program. In this case, what I'll show is a quick workaround for some of this information, which is that here in the United States, at the county level, there's GIS data servers that you can very often these days access. This map here is for Lane County, and it's hosted by the GIS Maps department of the county. And we can type in the address of our site, and we can select from a whole set of different map layers. Let's turn on an aerial base map. So for our aerial, oftentimes we can select from a whole set of different options. And again, these individual data layers can be also accessed from state governments and things like that to be incorporated into your own map if you're using a GIS program. So let's choose the latest there. We can kind of explore what option gives us the best resolution. Also, you'll see that there's wintertime and summertime maps. So this one's nice in that it tells us a little bit more about the riparian and oak woodland zones on the site, because we can see that the deciduous trees have lost their leaves in this picture. Here's one from the summer, and you can see that riparian corridor there. We can also add property boundaries. Here it is. So here's our site. We can add to this map topography. Now these are 20-foot contours. This is derived from the U.S. Geological Survey. So these contours are pretty old school. These days, we can also have access quite often to LiDAR, which gives us a lot more resolution on and accuracy for topography. LiDAR stands for light detection and ranging, and what it is it relies on lasers shot from airplane, which measure the light and the amount of time it takes for light to reflect back. And so you can target an object or a ground surface, and utilizing many millions of elevation points, that data can be organized in such a way as to show you the shape of the landform. It can give you ground level elevation data, which can be arranged into contour lines at any interval. And it can also give you canopy heights and the shape of structures and things like that if you pull out the highest hit points from your data set. So the Center for Rural Livelihoods is in Oregon, and a great source of LiDAR data for Oregon comes from the DOGAMI, which stands for the Oregon Department of Geology and Mining Industries. And they're a state department that, in part, has flown these LiDAR surveys all across the state. So you can use an interactive data viewer to find your location and source raw map data that you can use to generate your maps on GIS. When this quality level of data isn't available, there's other sources. For instance, there's a contour map generator that you can find online that uses Google elevation data to generate contours. So you can search your site and you can enter in different parameters from how many contour intervals you want, what intervals you want the contours at, the boundary of the site, to create a fairly accurate contour map. Oftentimes we can ask these data servers to also show us major waterways, lakes, and other rivers. And you can see here that what they're showing is only the first order stream. This is the stream that flows through the property in the main valley. But all of the primary valleys, there's 3 main ones, one here, and one here, don't show up in this case. That's because these are really just ephemeral, intermittent at best streams. Nonetheless, the place that we want to be really targeting for pond construction is not in a mapped waterway, but rather these tributaries which represent the primary valleys coming off of the main ridge. We can see that with the contours and the water lines, some of the vegetation that we were deciphering as potential riparian type vegetation is now coming into higher resolution. Let's take a look back at that wintertime map. We can see the stream corridor here full of its cottonwoods and alders and ash trees. We can see as well a bit of hardwood up here in this neck of the woods coming down through this little corridor. Not as easy to decipher any vegetation changes within this drainage, however. Nonetheless, if you were in the understory, you'd see that there was a lot of understory vegetation like vine maple and such that really highlights the presence of water in this zone as well. So let's now have a look at soils. And this too gives us a bit of a picture around the valley and ridge topography that we're working with on this site. We have more upland soils with the dotted orange polygon, 11E and 11D, while generally speaking, through these drainages, we have a different soil type. That's 43E. Now, we can get more information off of this program, but the best source of information for soils in the United States is via the USDA's Web Soil Survey. So we can click into the Web Soil Survey, and I'll just do a quick overview of the use of this program. So we can navigate to our site by address. This program doesn't have property boundaries, so you have to be pretty familiar with the boundaries if you want to select just this one property. But what we'll do is we'll draw a polygon around our area of interest. And once we've got the area of interest selected, we can turn it into a soil map. This shows us the 3 types of soil that we have on the site. We can pull up this information for these different soils to get a better sense of really what's going on there below the surface. So our soil that's located more at the toe and the foot of the ridge lines and in the channels is belt pine, silty clay loam. And there's 2 types of belt pine that are differentiated by the percent of slope. So we have a more gradual slope over here on the east side, and then these more pronounced ridges are steeper sloped belt pine soil type. We can click into this and pull up some more specific information that can be really helpful for us. We're kind of zooming in now from this 1,000-foot view to more granular level, but still we're at this point of looking at it from really just this like online resource level. We really also, it can't be emphasized how important it is to spend good time on the land and in the dirt, really seeing what the true conditions are. But this gives us a good sense of some of the potential. Our bell pine, which is generally the ridgeline soil, we can look into the typical profile. It shows silty clay loam down to 13 inches, silty clay to 34 inches, and between 34 to 44 inches is when we start to hit weathered bedrock. So this will be fractured bedrock, and probably within 2 to 3 feet, we would actually start to hit a bedrock layer that says depth to restrictive feature right here, 20 to 40 inches to paralithic bedrock. So that's going to be, a major determinant on the depth that we're able to build our pond. That's a pretty darn shallow soil. Further observation, digging test pits would give us a real sense of how deep that bedrock is. Another thing you might notice in here is the hydric soil rating. So this is basically, is this a wetland soil? The answer is no. There's more rules and regulations about building a pond or essentially doing removal and fill of soils on wetlands. So you're not going to be subjected to those concerns with this soil type, but also it's not a particularly wet ground by any measure of the imagination. Let's look at the Dixonville. This is the valley soil. So this soil reaches weathered bedrock again pretty quickly. This is a complex of soils. So a complex is basically a jumble of different soil types that occur in such a mix that it's really impossible to differentiate the soil at the site level. But generally, this soil has about 35% Dixonville soils, 30% Philomath, and 20% Hazel-air. What is important is that, again, this emphasizes the importance of doing that evaluation at the pond site with a test pit, because we may have any of these soil types in this complex. So the Dixonville has weathered bedrock at about 36 inches, and it is not hydric. Philomath weathered bedrock is even more shallow. It's also non-hydric. Hazel-air is a bit deeper, having weathered bedrock at about 46 inches. It's non-hydric. The depth to paralithic bedrock for Hazel-air is 40 inches, whereas the other ones, Philomath and Dixonville, are 20 to 40 inches. That gives us the start of a picture of our soils. We can also see that these soils grade as they go deeper into a higher clay content. Let's go a little bit deeper into this program to pull out particular soil data that we might want. Let's explore in a bit more detail some of the qualities of these soils for ponds. We can go to the Soil Data Explorer, and one useful measure is in soil physical properties, we can look at the percent clay. If we start by showing all layers, we get a weighted average of all the different soil horizons. And you can see that the percent clay for these three soils is 41.2 for bell pine and 41 for Dixonville. That's just getting into the range of an adequate amount of clay to hold water, a proper seal. It said 40% clay is the bottom end of the amount of clay that you want to have to work with to construct your pond. You'll need to be able to forage for the best clay to build the key and the non-porous section of the dam. If we have a look instead at not all layers, but the estimated subsurface soils that are going to have higher clay content, let's see what percent we get here. So this is showing 47.5% clay for the bell pine and 50% clay for the Dixonville Philomath Hazel-air complex. So here's our complex, and here's the bell pine soils. Complex is in the valleys and the bell pine soil on the ridge. Another thing we can take a look at is the suitability for constructing reservoirs. Go to water management, click pond reservoir areas. So this is showing very limited qualities for pond reservoirs. And now if we have a look at the basis that they use to come up with that, it has a low seepage potential in the upper 60 inches. It's determined by the hydraulic conductivity of the soil, the depth of fractured bedrock and other permeable material, and then also the slope, because the slope can affect the storage capacity of the reservoir area, but it can also affect the erosion hazard. So this just emphasizes how important it is to be really targeted in your selection of pond sites. That in general, most of the landform in this environment is not going to be ideal. And so we're going to want to be really thoughtful with slope, the soil conditions, and other factors to be sure that we're putting these ponds in strategic and wise locations. While we're here, we'll want to pop over to the Soil Properties and Qualities tab and find the hydrological soil group rating. Will help us figure out our runoff and discharge information for our pond further on down this planning process. So that should show a rating that is alphabetical, and these are estimates of runoff potential. So soil group A has high infiltration rate, which means it has a low potential for runoff. Soil group B has moderate infiltration. Soil C has slow infiltration. D is even more slow, very slow infiltration. These 4 types can be used to look at how much water can be assumed to be actually running overland versus infiltrating for your estimate of overland flow in your runoff calculations. So this soils data can be held alongside your map to help you have a better sense of the details around the suitabilities of your site for pond construction. Following this initial overview of the existing conditions on the land, another layer that's important for the base map is to identify all existing infrastructure. Sometimes this information can be found on these online GIS servers. Here's an example of the buildings. Some of the buildings have been mapped. You can also see them through the aerial image. You need to know what existing infrastructure you're working around as you're planning this integrated earthworks. So being able to map the roads, the buildings, and any other infrastructure is going to be important as well. So whatever point in the spectrum of tech you're working with to develop your base map, it's now time to compile all of the different layers that have been pulled together into a single map. And in my case, I will take all these layers, usually move them through GIS to make a final planning map. Here's an example of that map. And you can see it has topo and existing waterways. It also has the existing infrastructure and access systems and any pre-existing earthworks on the site. Soils are kept aside, in this case, just for simplicity's sake on the map. We can use this now to look for strategic pond locations. For the purposes of this exercise, let's move ourselves up into the northeast corner of the property where we can work across a series of ridgelines and valleys. Before we start to look at ponds, one thing that we should ask ourselves is, where are our zones of use? Where do we need this water to go? And beyond that, we should also be determining how much water we actually need for our use. So in this case, our zones of use are going to be right in here, as well as here. These are the locations of the main agricultural endeavors on the property. We need to site our ponds to service these areas. Another question that we should be asking is, what sort of access systems do we need to lay out that can overlap and also be in service to the pond system on site? In this case, the goal for access is twofold through the upper reaches of this property. It's to enable adequate access for forestry. Our only access presently is up into this section of the forest, and it's difficult to cross these drainages to get into other managed forest units, for instance here and here. So our needs for access are to have a an easily navigated access road that connects us through the site. And this access road also really establishes the line between upland forest and more intensive agricultural grazing and residential uses below. The road then becomes a fire break that differentiates these two environments, preventing fire movement from the forest or from the residential area into the forest, giving a good, manageable line with a natural fire break at that point. When we overlap this road with our earthworks, what we're doing is we're thinking about how the road functions as along a keyline pattern to differentiate that use in keyline between permanent upland forest and more open, gradually sloped, more usable agricultural soils below, and how the road can serve as a distribution for water, moving water from ponds to other ponds or moving water from off of the road surface to strategic pond locations. Finally, the road gives us a way to access pond water if we cross the ponds at the dams to take water out for firefighting purposes. So that's where the road also intersects with this. As soon as we feel settled on the general layout that we've come up with in our design process, we want to go from paper and take our evaluation to the ground, looking at every pond site on an individual basis and making sure that it fits the real world situation, looking at the soils, digging soil test pits, looking at the contour and the slope and the vegetation, and just making sure that the pond fits in the site and that it's an adequate spot for the pond. And we may find that we need to move them around a bit, move them up and down slope, or change their location altogether, or forego that location. Ultimately, once we've done that, we can come up with a final pond system layout. Before we get to work on the design and construction of the individual ponds, we'll want to do an analysis for each pond of the catchment, looking at what we can expect as far as flow volumes, how much water each pond can store, and what the discharge will be moving through the watershed, which will help us determine the size of our outlet pipes and spillways and trickle tubes.